Hello student, to the Foundation of Classical Electrodynamics course. Today we have lecture number 14 where we will going to continue the understanding of curvilinear coordinate system which we started in the last class. So today we have class number 14. We are studying curvilinear coordinate system. So in the last class we already mentioned that curvilinear coordinate system is a special kind of system where coordinates are defined in a curved space, not like we have in Cartesian coordinate system in flat space. So if I compare with the standard Cartesian coordinate system, x, y and z. So the any plane, if I draw any plane, it should be a very systematic, and this is a surface element we are having, and this is a flat surface where the coordinates are like this. Each point is a coordinate point and we can have a flat surface like this. On the other hand, for curvilinear coordinate system, this is Cartesian coordinate system. In curvilinear coordinate system, we can have a surface which may not be, which is a curved surface in general. So the surface should be something like this. So I have a like this and this, and then we have coordinate points like this. This is a just to show that how two surface differs. We have a plane surface here and curved surface here. Like x, y, z, here we have u1, u2 and u3 with the unit vector e1, e2 and E3, a generalized form to write the unit vector because I am taking a generalized coordinate system. However, this condition is valid here. They are orthonormal system. Okay. So in this coordinate system, if I now in Cartesian coordinate system, if I want to find out what should be my length element, it is very straightforward, and which is dxi plus dyj plus dzk. However, if I want to find out the length element here in this coordinate system, it is not like this. We have a scale factor, last we mentioned that, and it will be something like h1 du1 e1 plus h2 du2 e2 E1, E2, E3 are unit vectors, and H3 DU3 U3. If I find out what is this value, say ds square, here we simply have dx square plus dy square plus dz square. On the other hand, here if I calculate ds square, then it should be h1 du1 square plus h2 du2 square plus h3 du3 square of that. So, this is the way we defined the square of the length element, and if I compare these two, because Cartesian coordinate system is a general is a special form of the generalized version of curvilinear coordinate system. So, if I compare these two, then I can readily have the value of h, the scale factor hx, hy and hz is equal to 1. So, that is the value of the scale factor for Cartesian coordinate system that we derived last day also. Also, we have a recipe, we used a recipe to derive this scale factor, and that recipe also you can use, and we calculated that this recipe, and that recipe, if I write once again, that if I want to find out the scale factor hi, then that value should be figured out by using this expression. So, the value, the function if you know in terms of h1, h2 sorry u1, u2, u3, y as a function of u1, u2, u3 and z as a function of u1, sorry then you can figure out what is the value of this scaling factor. Last day we derived that, but also you can by comparison you can also find out the scale factor. So, for example, I can give you a simple thing, like for already I compare here the Cartesian coordinate system with the generalized curvilinear coordinate system, and this from this length square expression I can find out the value of h1, h2, h3 should be this one. In the similar way, for cylindrical coordinate system, for a cylindrical coordinate system, so for cylindrical coordinate system we have a system like this. And any point here if this is rho, this is phi and this is z. So, any point here P can be expressed in terms of rho phi z, and the distance element. So, this is the coordinate, and the distance element I can write simply ds is d rho unit vector plus rho d phi unit vector plus dz z unit vector. Similar way, if I calculate the square of this quantity by making a dot product with the same thing, then it should be simply the square. Then you find that it should be d rho square plus rho square d phi square plus dz square. And now if I compare this equation with whatever the expression we have here, that is this one, this is the generalized expression we are having, this is the generalized expression. Then if I compare, then readily you can see the value of h rho seems to be 1, the value of h phi is rho, and the value of h z is 1. Exactly the same value we derived in our last class, but we during that time we use this expression. You can do both the ways. And now this is for cylindrical coordinate system, but for spherical coordinate system we can do the same thing. Let us simply draw the spherical coordinate system. So, any point here over some, so I can have the r value here, so this is phi and this angle is theta and this is r. So, the value of p here, whatever the point we are considering, p, which is r theta phi, for this coordinate system, if I write the distance element like the way we did, we know that how to write the distance element in different coordinate system. So, ds. So, this value if I write, it is dr r unit vector plus r d phi r d theta unit vector and r sin theta d phi unit vector. Again, making a dot product, we can have d square is equal to dr square plus r square d theta square plus r square sin square theta and then d phi square. Now, again if I compare with this this generalized expression for curvilinear coordinate system that we have here, ds square. So, I can compare and I find that h1 in this case hr is equal to 1, h theta is equal to r and h phi is equal to r sin theta. Okay. So, you can also calculate this by exploiting this expression here. say the equation 1, if I write this equation 1, you can also find out the value of this h1, h2, hr, h theta, h phi by exploiting this expression 1. Okay. That is the thing we did last day. Also, in the last class, we figure out the expression of the divergence in curvilinear coordinate system. So, the expression of the divergence no, not divergence, we did the gradient. Divergence we will do today. The gradient so the gradient is in curvilinear coordinate system. If I want to find out the gradient, the expression that we figure out is this. This is the operator operating on a scalar field f, and if I want to find out the ith element, it simply gives us h I and then del f del ui. Okay. This is the expression we figure out, this is the generalized expression. Now, for these 3 coordinate system, I know the scaling factor. Starting from the Cartesian coordinate system, here I know the scale factor for cylindrical coordinate system and spherical coordinate system. So, using that you can figure out what should be the expression of the gradient in these 2 specialized coordinate system, cylindrical and spherical. So, this is a most generalized form. So, you can exploit that. So, today we will extend this thing and try to figure out the expression of. So, today we will calculate the expression of divergence. Divergence. How one can express divergence in this curvilinear system. Okay. So, let me draw once again this figure for curvilinear coordinate system. So, the figure means this the volume element, that we draw last day. So, I am using this okay. So, this weird looking system where okay, I should have one line here also. So, the coordinates are like this. And here I should have so, this is my u1 having unit vector ei, that is my u2 having unit vector e2, that is my u3 having unit vector e3 along this direction. Okay. And these if I now calculate these lengths, so from for example here to here, this is d this length is ds2 and that value is h1 with the scaling factor, that is the important du2. This length from here to here is ds1, which is h1 du1, and this length is ds3 is h3 and du3, that we already defined last class, and this is the origin O, this is the origin O. Okay. Now, we will going to this is the coordinate system I am having, and now I want to find out what is the expression of the divergence. So, let us go back to the the theorem that we had, that the divergence theorem, and that is, if I have a divergence of a vector field, say f here, which is a vector field, and then integrate it over a volume, then that value this value should be equivalent to the closed surface integral of f dot ds. This is a surface, not the length element, mind it. So, better I just remove this to make it surface, otherwise there might be some confusion. So, this is dA, mind it, this is the dA, which is the surface element. Okay, that is the expression of, this is the volume integration and this is the surface integration, and that is basically the divergence identity, the divergence rule that that we proved. And now I am going to exploit this to find out this expression. Now, this expression left hand side if I write, and then right hand side I calculate for this given volume, and then we will find what is there. So, left hand side if I write simply divergence of f and dV, it should be this flux. So, I am just calculating this flux, I am not going to integrate and calculate this in the right hand side. So, I have this volume element, whatever the volume element is shown here. So, I need to integrate it over this surface, whatever the surface. So, again we have 6 surface here, and for this 6 surface if I calculate the right hand side, that I am doing, I am going to calculate this for this surface, I will calculate the right hand side, that is this integral. So, the value, the first I calculate the value of, say f is a vector field, and this vector field, if I define here, it is f1 and then unit vector ei plus f2, then unit vector e2 and f3 unit vector e3. F is a function of the generalized coordinate here, whatever u1, u2, u3. It may be xyz, it may be rho phi z, it may be r theta phi. Okay? I am just writing in a generalized way. Now, when you calculate, so you calculate the divergence for each surface, you need to calculate, and if I do, then for the first surface I will have f1 is along this direction, in this direction. So, I will take account this surface, whatever the surface is here. So, for this surface I have this length element, and ds1 and ds3. So, that we will going to exploit, that I will going to put, but the scaling factor is there. So, I need to calculate this scaling with this scaling factor. So, h1 sorry h okay, here I am making a, this should be h2, I am making a mistake here, h2. Okay, so f1, then this h2 h3 at which surface? The surface that is here. So, this surface is at u1 plus du1, okay, at this point. Then another surface, the opposite one, is sitting here in this region. So, I can write f1, the negative sign is because now the direction of the surface is reversed. So, I should have h2 the scaling factor, h3 the scaling factor, but I am going to evaluate at du 1, and then I have the surface because du 2 and du 3 is the surface element if I just multiply. So, what is the surface element here for this particular surface? I am just showing one. So, the surface element dA, and that should be the vector sign, and this value is simply, this one is simply h2 h3 du2 du3. In a similar way, rest of the surface you can calculate. Now, this is a unit vector. So, this if I consider this one, it should be a unit vector of ei. This one, opposite one, this one should have a unit vector with minus ei. So, that I am just writing here. Okay. Then I will add similarly, once you understand that, the similarly the rest thing is mechanical. I should have f2 3 1 evaluated as u2 plus du2 point minus f2 h3 h1 evaluated at du2, and the surface element I am calculating 2. So, it should be 3 and 1. The last one, f3 and h2 h1 evaluated at 3 3, and then I have f3 h2 h1 evaluated at u3 with 1 and 2. Now, these I simply evaluate, and the volume element, now if I understand the surface element, the volume element, simply let me write here, for this curvilinear system is simply h1 du1 h2 du2, everything is same except the scaling factor. You just need to incorporate the scaling factor, that is all, u2 and h3. I am having an issue here with the pen. h3 u3, this is 3. Okay, so eventually I should have h1 h2 h3 to H3 multiplied by du1 du2 and du3. Okay. Now, after just doing this calculation, it is evaluated at u plus d ui and it is calculated at duy. So, I can just expand this is the Taylor series. So, that if I do, I will simply get this one. So, this is a volume element. So, simply I will get this one. So, left hand side I will get this. Dot, and that is 1 divided by H1, H2, H3, and these things is not equal to multiplied by d u1 f1 h2 h3. I don't know what is going on here, and then plus d u2 and then f2 h3 h1 and plus d u3 f3 h1 h2. This is 2. So, I don't know, I mean pen is not working properly anyway. H2. So, these things are important. I mean once you have this expression, then it is clear that in generalized form, if you know H1, H2, H3, then you can find out what should be the form of this divergence in any coordinate system. You can see there is a significant difference between the Cartesian coordinate system to spherical polar coordinate system to this. Now, after that I will include another very important operator. Let me go to the next page, and that is Laplacian. Okay, I don't know. So, the Laplacian operator is defined in this way. I have a dot product here. And okay, please note there is a dot here. I don't know, dot is not. And then this operator is already calculated. It is H1, H2, H3, and then DUI, just we calculate DUI, the ith one, and then Hj, Hk. If it is I, you can see that once you make a derivative 1, then the scale factor is 2 and 3. Here if it is 2, then scale factor is 3 and 1. That is why if it is I, then it will be j and k. So, that is the form we are having. Now, if I calculate, if I find out what is the form of the gradient of ith element, then it should be 1 divided by h I of this is not, and then del f del u I. Okay. So, if I combine these two, I should simply have, it is the ith of this and ith of this, because this is the way defined, it is I, and that thing is equal to 1 divided by h1, h2, h3, and then sum over d u1, because there are I j k. So, I should write I here, j here and k here, and rest of the term what we have is h j, h k and divided by h I, which is here, and then del f and then del u I. This is the generalized form. So, I will show you later in the next class, maybe in an explicit way, for different coordinate system how you find these values. So, Laplacian, you may remember that you can define the Laplacian by the divergence of a scalar field and then take the gradient of a scalar field and then divergence of that. Now, I calculate both the expression here, I calculate the divergence and the gradient last day. So, this is the expression of the gradient and this is the expression of the divergence. If I want to find out the ith value of the divergence, if I calculate what is the ith form of the divergence, then it is simply I, this is I j, sorry, this is I j and h k, and then this is del, if it is ith, then it is I and it is operating over f. So, it should be h, then j, k and f I. This is the way we can define the ith component of this divergence operator, and we mix up this thing here in calculating the Laplacian. If you mix this thing, then first you have this the divergence, and then we have the the gradient, and then if you put this, since we have a summation, because for every ith you have I j k, that this will be there. So, this is sum over the cyclic. So, I should write it here. This is sum over the 3 cyclic cyclic permutation of 1, 2, 3. the cyclic permutation should be. So, once it is 1 2 3, then 2 3 1, then 1 2 3, then 3 1 2. So, today I do not have that much of time to discuss more about this Laplacian operator. Maybe in the next class I will define again, I will discuss again the Laplacian and then curl, and then jot down finally what should be the general form of all the coordinate system with this operator: gradient operator, divergence operator and curl operator, which we already defined earlier. Again we will do, but in the form of, in the generalized way, by just understanding the curvilinear coordinate system. So, with this note I would like to conclude today's class. Thank you very much for your attention and see you in the next class.